You have seen the Submarine movie. The crew is packed into a metal tube somewhere beneath the Atlantic. Faces are pale, the air feels thick. Someone checks a gauge and announces they have maybe 48 hours of oxygen left. The captain makes the hard call. They surface. They survive. Credits roll. Here is what that movie never explained. The oxygen was not the problem. The submarine was not out of air. It was not out of power. It was not even close to its operational limit. The crew surfaced because their food ran out, or their deployment ended, or command ordered them home. The boat itself, the actual machine, could have stayed down for years, not weeks, not months, years. And the reason has almost nothing to do with how much air is inside, and almost everything to do with a reaction happening inside a reactor roughly the size of a kitchen table that requires no fuel deliveries, produces no exhaust, and generates enough heat to power a city block continuously for decades. This video is about the physics the Navy never fully explains. Most people assume a submarine is limited by air and battery life, the same way a diver is limited by what is in their tank. That assumption is completely wrong for nuclear submarines, and once you understand why, you will never watch a submarine film the same way again. We are going to cover 4 things: how a nuclear reactor actually works inside a submarine, how the boat makes its own oxygen from seawater, how it manages pressure, heat, and carbon dioxide in a sealed metal tube, and why the only real limit on how long it can stay down is the crew, not the machine. Start with the reactor because everything else flows from it. A nuclear submarine does not burn fuel the way a car or a diesel-powered vessel does. Burning requires oxygen. Oxygen is exactly what you do not have unlimited access to when you are 800 feet underwater. A nuclear reactor does not burn anything. It splits atoms. Here is the simple version. The reactor core is loaded with enriched uranium. Uranium atoms are unstable. When a neutron strikes a uranium nucleus at the right speed, the nucleus splits. That split releases energy, enormous amounts of it, plus 2 or 3 additional neutrons. Those neutrons go on to strike other uranium atoms, and those atoms split. More neutrons, more splits. This is the chain reaction. It does not require air. It does not require combustion. It requires only the uranium and the geometry of the core to sustain itself. The energy released by those splits comes out primarily as heat. That heat is used to boil water. The steam from that water spins a turbine. The turbine drives the propeller and the generators. The generators power everything on the boat: the lights, the electronics, the life support systems, the cooking equipment, the navigation computers, all of it. The reactor on a Virginia-class submarine produces roughly 40,000 shaft horsepower. For comparison, the engine in a Formula One car produces around 1,000. A single nuclear submarine reactor is putting out the equivalent of 40 Formula One engines, simultaneously, continuously, from a core that has not been refueled in over 25 years. That is not a misprint. Modern naval reactors are designed to last the entire operational life of the submarine without a fuel change. The USS Virginia was commissioned in 2004. Her reactor core will not need refueling before she is decommissioned. 1 load of fuel, 30 years of operation. But here is the part that actually answers the question about staying underwater. Because the reactor produces power without requiring any outside input, no air intake, no exhaust pipe, no fuel deliveries, the submarine is energetically self-sufficient. It does not need to surface to recharge batteries the way a diesel submarine does. It does not need to run a snorkel to the surface to breathe. It generates its own power continuously, at depth, indefinitely. That solves the energy problem completely. But energy alone does not keep a crew alive. The crew needs oxygen. Here is where it gets genuinely remarkable. The submarine makes its own oxygen, not from tanks, not from compressed as cylinders brought aboard. It manufactures oxygen from seawater using a process called electrolysis, powered by the reactor. The principle is straightforward. Water is H2O, which means 2 hydrogen atoms bonded to 1 oxygen atom. If you run an electrical current through water, you break those bonds. The hydrogen goes one way, the oxygen goes another. The oxygen is pumped into the boat's atmosphere. The hydrogen is vented overboard. The machine that does this is called an electrolytic oxygen generator, but the crew calls it the electrolyzer. It runs continuously. It takes in seawater, splits it, and releases breathable oxygen into the air supply. As long as the reactor is running, and the reactor is always running, the submarine can generate oxygen indefinitely. That is important, but if oxygen generation were the only challenge, this would be a short video. The harder problem is carbon dioxide. Every breath a human takes in pulls oxygen. Every breath out pushes carbon dioxide. On the surface, that carbon dioxide disperses into the atmosphere. In a sealed metal tube with 130 people inside, it accumulates fast. At high enough concentrations, carbon dioxide does not just make you sleepy. It causes confusion, then incapacitation, then death. The submarine solves this with a system called the carbon dioxide scrubber. The scrubber circulates the boat's air through a chemical compound. Monoethanolamine is the one most commonly used. It absorbs carbon dioxide the way a sponge absorbs water. The carbon dioxide bonds to the chemical. Clean air comes out the other side. Periodically, the scrubber regenerates by heating the compound, which releases the captured carbon dioxide as a concentrated gas that is then vented overboard. The system runs continuously. The reactor powers it. The crew breathes. But there is a third atmospheric problem that almost nobody talks about. Hydrogen. The same electrolysis process that makes oxygen also produces hydrogen as a byproduct. Hydrogen is extremely flammable. In the right concentration, it is explosive. Inside a sealed submarine, that is not a theoretical concern. It is an active engineering problem. The solution is a device called the hydrogen burner, more formally the catalytic recombiner. It takes the hydrogen produced by electrolysis and combines it with a small amount of oxygen in a controlled reaction, converting it back into water vapor before it ever reaches dangerous concentration levels. So the submarine is simultaneously making oxygen from water, scrubbing carbon dioxide from the air, and converting hydrogen back into water, all running in parallel and all powered by the same reactor that is spinning the propeller. The atmosphere inside a nuclear submarine is not natural air, it is engineered air, manufactured and maintained by machines around the clock for months at a time. That leaves one question: what actually limits the mission? Not power, not air, not water. The submarine distills fresh water from the ocean for drinking and cooking, not even propulsion. The limiting factor is food. A submarine loads enough food for 90 days before deployment. The crew eats 3 meals a day. The food takes up physical space. When the food runs out, the mission ends. Not because the boat has failed, because the crew cannot be sustained any longer. The second limiting factor is the crew themselves. 6 months in a sealed metal tube, cut off from sunlight, operating on rotating watch schedules, under the constant low-level stress of operating in a hostile environment. That takes a measurable psychological toll. The Navy manages this with everything from structured routines to movie nights to carefully designed lighting systems that simulate a 24-hour day-night cycle. But there is a limit to how long human beings can operate at peak effectiveness in those conditions, regardless of how well maintained the boat is. The submarine could keep going. The humans need to go home. Here is what that means in real numbers. The longest submerged patrol on record was made by HMS Warspite, a British nuclear submarine which stayed submerged for 111 days in 1982. More recently, USS Providence completed a deployment that kept it submerged for extended periods without resurfacing. The operational standard for most nuclear submarine deployments is somewhere between 70 to 90 days submerged. Not because the boat is running out of anything, but because that is the human limit the Navy has determined for sustained, effective operation. If you remove the crew and ran the submarine unmanned, which is obviously not how it operates, but follow the physics, the reactor would continue running. The oxygen generation would continue, the scrubbers would continue, the submarine would sit at depth, fully operational for years until the mechanical components required maintenance that could not be performed automatically. The machine outlasts the people inside it. every time. If this kind of deep physics breakdown is what you are here for, there is a lot more where this came from on this channel. Subscribe if you have not already, because the next video covers something just as counterintuitive. Here is the part that should stay with you. We started with a submarine movie. A crew counting down their last hours of breathable air, a dramatic surfacing, the machine at its limit. The reality is almost the opposite. The machine is not at its limit. The machine is barely challenged. It is splitting atoms, generating electricity, manufacturing oxygen from seawater, scrubbing the atmosphere clean, and could continue doing all of that for years without a single resupply. The crew goes home because humans need sunlight and fresh food and the surface world. The submarine stays ready. That reactor, the size of a kitchen table, running silently 800 feet below the surface, asking for nothing from the world above, is one of the most extraordinary pieces of engineering in human history. Most people who have seen it depicted on screen have never been told how it actually works. Now you have.